Okay, works. Okay, come. Let's start for today. Okay, we're gonna start on a new topic. This is the last topic we're gonna do for the month, basically until next year. Okay, Arenes. We've done alkanes already. Okay, Arenes last one for the year. Okay, 3 lessons for this. Okay, so come. We're gonna start off with what Arenes is all about first. Okay, today we'll be discussing this thing called a benzene ring. Okay, I'm sure you have seen a benzene ring multiple times, but we are gonna finally know what it's actually about. So we're going to spend a chunk of time describing benzene, its origins, why it's so special and all that. Okay, so benzene is a compound that has C6H6 as its molecular formula. Now guys, why is this weird? Because when this was first discovered, okay, can you all just tell me what's the general formula of an alkane? Remember? Alkanes. CN H2N plus 2, in fact. Okay, then for alkenes, CN H2N. Okay, so generally speaking, most hydrocarbons have at least twice the number of hydrogens. But then suddenly, right, you can have the carbon and hydrogen in a 1-to-1 ratio. How is that possible? Right, okay, then that's when scientists realize the only possibility for this to happen is if they arrange 6 carbons in a cyclic structure, and furthermore, you can have 3 double bonds in the structure. And the double bonds, as you can see, they're alternating. Okay, you won't really see 2 double bonds side by side. So this actually is so-called the initial structure of benzene when they first discovered it. Okay, as you can see, guys, each carbon has 1 hydrogen only. Right? All of them have 1 hydrogen, so C6H6. Okay, but this is where things get a little bit tricky. Okay, scientists start to realize, right, that benzene can also exist as this compound instead. Okay, now I just need you guys to take a look at the difference. Some of you guys will tell me there's no difference, what? Right? Again, I can just rotate this a little bit to the left and I get this. Okay, but just bear with me for a moment. Later I'll explain why. But this is actually a different structure compared to this. Okay, it's not that I just rotated it. The double bonds positions, as you can see, are different. Okay, so what's happening over here? Benzene can exist as 2 different structures. Okay, so what is the structure of benzene like? Okay, so that's why the scientists, right, okay, they actually came up with basically a compromised structure. This right here should then be the structure of benzene from now on. Okay, this kind of takes both structures into account now. Like 1 second they exist like that, the other second they exist as this. Then it keeps alternating between them. Okay, so it keeps alternating between the two. They don't want to have any trouble already, right? So they just added a ring in the middle of benzene, and that's how the structure of benzene came about. Okay, makes sense so far. We will then understand what this little ring is here for. Okay, but any questions so far? No, okay, so you can turn over to the next page. Okay, so on the next page alone, right? Okay, there are a few things here. Okay, you all just look at the point first. This one we're gonna look back all the way to hybridization. Okay, so let's talk about hybridization first. Okay, can you look at each carbon atom? Okay, I know you're not very used to this yet. Okay, so perhaps you can look at one of these guys. Can you tell me each carbon has what shape? What's the geometry around each carbon? Tetrahedral, trigonal, planar, or linear? Okay, you can just pick up one random carbon, they're all the same. Okay, good. There's a double bond here, and then there's 3 bond pairs, right? Okay, so each carbon, right, is actually a trigonal planar shape. So guys, can someone tell me what's the hybridization of this carbon? Okay, sp2. All the carbons here, right? Okay, all carbons are sp2 hybridized. Now, just a very quick recap of hybridization, right? I'm just gonna take out one of the carbons and let's just draw them over here. Okay, this right here is a trigonal planar carbon. Hello, sir. What nice string. Nice string. This is a very nice shirt. This is a nice shirt. Party, the competition is a party shirt. Okay, so anyways, as I was saying, every single carbon atom is same in a benzene ring. It is sp2 hybridized because all of them are trigonal. Got that so far? Okay, look at that trigonal planar carbon. Let's zoom in. Okay, first of all, can we identify the number of hybridized and unhybridized orbitals? First of all, how many sigma and how many pi bonds are there on each carbon? How many sigma bonds are there on this carbon? 3. Okay, 3 sigma and how many pi? 1 pi. Okay, so remember, Sigma bonds, how do they overlap? Head on. Okay, so what kind of orbitals overlap head on to form a sigma bond? The hybridized one or the unhybridized one? Okay, hybridized orbitals. Hybridized orbitals overlap head on. Okay, so perhaps I'll write this down first. If I have 3 sigma bonds, how many sp2 hybridized orbitals do I have? 3 also now, right? Okay, it has to be the same. So I have 3 sp2 hybridized orbitals which overlap head on in order to form sigma bonds. So take note, only hybridized orbitals can overlap head on to form sigma bonds. Okay, and on the other hand, now we have pi bonds, right? If you have one pi bond, then that means you have what? You have one what orbital? Okay, one orbital, p orbital, yes. Okay, because these p orbitals overlap sideways to form pi bonds. Okay, so remember these facts again. You can only have hybridized orbitals overlapping head on and p orbitals overlap sideways to form pi bonds. So we know that every single carbon atom here has 3 sp2 and 1 p orbital. All got that so far? Hybridization, again, nothing new yet. But now we link it back to the benzene ring. Okay, in this benzene ring, guys, all the carbons are sp2 hybridized. Okay, but what I'm interested in now, guys, I'm not interested in the sigma bonds. Okay, y'all look at my fingers here. These sigma bonds, both cases of benzene ring, right? They all are sigma bonds, correct? But what I'm interested in are the pi bonds. Because for some odd reason that we do not know yet, the pi bonds can somehow appear on different positions. We do not know why it can do that yet. Okay, but can you all see what I'm trying to get at? I'm more interested in only the pi bonds because these guys somehow can change positions. So let's not care about the sigma bonds. In other words, if all the carbon atoms are sp2 hybridized, each carbon atom has one p orbital. Can see that. I'm more interested in this fact because I somehow want to explain, right, why benzene has this little ring in it. And so far. Okay, so let's draw a very big diagram. I know it's in the notes also. Okay, but just follow me through this. Okay, look at all these sigma bonds. Again, I don't care about these sigma bonds. But what I care about are the p orbitals. All carbon atoms have one, right? One each. Okay, so I'm going to draw one p orbital on each carbon atom. 1, 2, 3, 4, 5, 6. Now, guys, I just want you all to focus on the left structure. Ignore the right one first. Can you all see the left structure here? A pi bond is formed between these two carbons. So that means, right, the p orbitals are overlapping sideways like that. That's how we form that first pi bond. All agree first. How about this second pi bond is between these two guys, right? So then they overlap, and then the third one's over here, overlap, and overlap. So that's how I can have these 3 pi bonds. Agree? Now, guys, are electrons stationary or are they moving? Okay, focus on these pi electrons. Electrons are always moving, right? So do you think the electrons are just going to stay here, here, and here? No. Now, why is it that electrons can basically fly to another position? Look at the p orbitals over here. Is there anything stopping these two p orbitals from overlapping? Is there anything stopping these two from overlapping? And same thing for these two. No, they're all side by side. So imagine this. Imagine you have 6 people standing in a circle. Are you just going to hold hands with the person to your left and not to your right? No. Okay, you can hold hands with both the person on your left and on the right because you're all standing next to each other. In other words, what I'm trying to get at is this. All these p orbitals, they are all in a circle and they are all side by side. So in other words, they can all overlap in one entire big happy family. They will all overlap like this. So you can see that. Imagine 6 people all holding hands with one another. They're all connected, right? One big circle. You can see that. So when this happens, guys, do the electrons just stay on this, and this position? No. Okay, they are all connected. So the electrons can just fly and travel around this entire benzene ring. You can see that. So one moment the pi electrons can be here and here. The next moment it can be here and here. And then it can keep alternating. The electrons can just keep jumping all around each other. And that can happen because the p orbitals overlap continuously. Okay, so that's the key word over here. Each carbon atom has a p orbital. So there is a continuous overlap of p orbitals. The key word here is continuous. They will all overlap one another like one big happy family. Okay, can see what I'm trying to drive at? Okay. So because they can overlap each other like one entire loop, the electrons, the pi electrons, can basically, what's this? What's another word for electrons traveling? It's like delocalize. Electrons are free to delocalize across this entire benzene ring. Nothing is stopping it. So you shouldn't look at it as pi electron here, 2 here, 2 here, 2 here. It should be 6 pi electrons all in the ring. See that? So that's what we are trying to drive at. You can't draw this structure, you can't draw this structure. You must draw the circle. Because this circle represents, I say here now, this circle represents what we call a delocalized high electron cloud. Now, these 4 words I'm going to be repeating throughout the entire lesson. Is that important? I say again, okay, let's explain how this works. Every carbon atom has a p orbital, as shown in this big diagram here. They can all overlap continuously, allowing the electrons to delocalize across the entire ring. So this creates what I say, I repeat one more time, a delocalized high electron cloud. Okay, I'm aware that your school has covered this topic also. Okay, but I'll go through this part, especially slower. Okay, that is very important. Okay, pi electrons always moving. And now they have the chance to move around the entire ring because everyone is connected with one another. All the carbon atoms, all connected with p orbitals, all continuously overlapping one another. That's why electrons, given their ability to move around, okay, it will just move keep going. 6 pi electrons freely moving across the entire ring. Okay, creating this thing here. Okay, so these 4 words, pay attention. Later we'll be discussing what this is about. At the moment, any questions? Okay. Hey guys, so what? What's so special about this little circle? What's so special about the delocalized pi electron cloud? This delocalized pi electron cloud, guys, just take note. It makes benzene extra stable. Okay? It makes benzene very and extra stable. That's why benzene is such a special compound. It's not like any other alkene, alkane, none of that. It is so special because it's super stable. Why is it stable? It's because of this guy, these 4 words, delocalized high electron cloud. Okay, it is so stable, right? Okay, there's another term for this. I want you to write down also. Okay, benzene is resonance stabilized. Okay, so I know you will see these words thrown around in your school's notes or whatever. You will see the word aromaticity or whatever, okay? Resonance. Okay, we'll explain resonance in the topic. But resonance just means delocalization. Okay, it's stabilized with delocalization. Stabilize using this delocalized high electron cloud. That's just what it means. Okay, fancy words here and there. Okay, all okay so far. So I've just proved one point. Benzene is a very stable compound because of the entire process. All okay so far? Okay, so you can jot down whatever you need to. Okay, it's also shown on that page. Okay, but I suggest you can draw it out yourself. Any questions? Okay, if no questions, okay, I'll need the space because if you all turn over to page 4, okay, there's a diagram there. I'm going to draw it inside also. Okay, I erase this up, right? Okay, so guys, there's going to be a type of question where you see an energy level diagram. Turn over to page 4. On page 4, you can see the energy level diagram, but don't worry, okay, I'll draw on the board. I just need you all to follow me on the board. Okay, now this energy level diagram is going to show us, right, how the ring, the delocalized high electron cloud, can make benzene extra stable. How do we know that? How did scientists figure that shit out in the first place? Okay, so it is through this energetics diagram. Okay, so I want you to focus on this, right? Now, first of all, this is what's going to happen. I'm going to take this compound here. It's just a normal cycloalkene, okay? And then I'm going to add hydrogen gas. Guys, what's going to happen now when I add H2 gas? Alkene turn back into what? Alkane. Yeah, okay, so this reaction here has an enthalpy change of -120. Okay, just look at the value first. Okay, again, you're not required to draw out this diagram. You just need to know how to interpret this. Can so far? Okay, can okay, now I'm going to take out this compound instead. I have a compound with 2 double bonds. How many hydrogen gas do I need to get this? This guy have 1 alkene. I need 1 hydrogen to turn back into an alkane. But I want to form this same guy. I need how many? I need 2 long. Okay, I have 2 double bonds. I need 2 H2 gas. Guys, I want you to make a guess. What do you think is the enthalpy change here? Okay, about -240, right? Okay, so it is true. It's about -237, very close. Very close. Okay, so how about this guy? Now, as you can see, guys, how many hydrogens do I need for this structure? Is this benzene? Okay, no, it's not benzene. Take note. This right here is known as the theoretical structure of benzene, not the actual real life structure. So theoretically, because last time a lot of scientists think that this is benzene. Okay, so we have this. Okay, what do you think is the value here? 120, 240. We expect this to be 360. Okay, so this is what the scientists have thought. They expect this when you take benzene and then you react with 3 hydrogen gas. They expect it to be 360. But when they actually took benzene and they do this same reaction here, so the actual structure of benzene has a ring. The value that they measure is only -207. What on earth is going on over here? This is what they theorized, but this is what actually happened. Why is the value here so much less than what they predicted? So first of all, I need you all to write down a few things that we learned in energetics. Okay, go back to energetics, guys. And you all realize this. The lower you have, the lower energy level, are you more stable or less stable? More stable, good. Imagine a child, an ADHD child. Okay, he just woke up. You don't have that much energy, right? Okay, still a bit tired. You think he'll be flailing all about? No, it's very easy to control such a stable kid, right? Okay, but you compare it to the other side. Imagine the child has been awake for a while already. He has very high energy level, just jumping all about. You think that guy is very stable? You think very easy to control? No, he's very unstable, right? So I need you to remember this principle we learned from energetics. The lower you are in the energy level, the more stable you are. Okay, so you must go low lah. Okay, can? Now guys, compare the theoretical structure and the actual structure. Who is more stable? Look at the diagram here. Based on our results, who is more stable? The theoretical or the actual structure? Okay, the actual structure is more stable, right? It is more stable than what was expected up here. And guys, I need you guys to ask yourself the same question. What's the difference between the theoretical and the actual structure? What does the actual structure have that the theoretical structure does not? Okay, what are the forwards? Delocalized, high electron cloud. The actual structure has this thing, right? Which makes it more stable in the first place. Okay, so you look at it. It's more stable because it has a lower energy level. Why is he more stable? It's because this guy has delocalized high electron cloud. The theoretical structure don't have such a thing, as you can see. And because of that, that's why it has a lower energy level. So from this diagram alone, we can actually justify that the delocalized high electron cloud makes the thing extra stable. Okay, we still have another question to ask, right? But understand this first. It's at the lower level, so it's more stable. Why is he more stable? It's confirmed because of this guy here. Next, guys. Can someone just tell me, right, how much energy is used to stabilize this compound here? How do we calculate the amount of energy used to stabilize this compound? It's just a difference, right? Okay, good. So in other words, guys, the difference between these two levels here is known as the delocalization energy. In other words, it's just the energy to stabilize the benzene. Okay, so you can minus it off. What's the value here? Okay, just go minus it off. Okay, then you can find the value. Okay. Okay, so they've calculated the delocalization energy for you guys already. Okay, it's over there. But I hope you all realize this is the amount of energy needed to stabilize benzene. All okay? Right? So you don't have to draw this in the exam. You just need to understand how this works. Is that the McCarthy chat? Oh yeah. That's not my size. That's not very cute. Oh, that's weird. Yeah, Japan is the best. They have the banana cake. That's not bad also. Yeah. Okay, guys, any questions here? Can? Okay, so if you turn over to page 5, right, it's just whatever I discussed. Okay, but then if you forget, then it's over there. Okay? Okay, take note whatever you need to first, okay, before we move on to the last segment. Okay, then we'll spend a bit of time also. We'll look at some applications. Okay, so far we have discussed benzene is very special. Okay, because you can have this delocalization thing that no other compound has. Okay, so that's what we explained already. Okay, so we already mentioned delocalized pi electron cloud. What's the primary function? What's the primary benefit for benzene? Less stable. It makes it a lot more stable. Okay, so that's like a primary function, but okay, there's other functions also lah. Okay, there are other secondary benefits that comes along with a delocalized pi electron cloud. And the first one that we're going to discuss, okay, turn over to page 6, okay, is the fact that they have identical bond lengths. All the carbon-carbon bond lengths in benzene are exactly the same. Now, some of you may be like, isn't that obvious? Because it's a freaking bad hexagon. Hexagon must be all sides the same one, right? Okay, but not necessarily. Okay, we must explain why they all have the same bond lengths. Okay, because once again, guys, this delocalization, okay, pretty much just ensures that all of them have the same bond lengths. Okay, that was not really the important part. Okay, but basically remember all your p orbitals overlap. Okay, so the pi electrons exist all right in the ring. Okay, but I'm not really concerned with them being all the same. Okay, I'm more concerned with something else. Okay, so if you want to take a look at the second bullet point, the bond length is in between that of an alkane and alkene. Okay, so let me just give some fake values. Okay. Let's say this is 0.154 nanometers. In an alkene, a double bond is 0.120 nanometers. In a benzene, okay, I just write here CC in benzene. This bond length could be somewhere in between. Let's say 0.140. Our job here is to explain why. Now remember, a benzene ring is pretty much just made up of either a single bond or a double bond. Right? Now, first question is this. Why do they have identical bond lengths in the first place? One of them is double, the other one is single. Shouldn't double and single be different lengths, right? But remember, it's not just double and single. Okay, benzene exists all at the same time, right? Okay, that's why it's not just considered double and single separate. Okay, it's considered as one bond length. That's why it's all the same. But the second question is, why is it in the middle of a single bond and a normal double bond? Now, first of all, you all just imagine it this way first. I want you to focus on this bond over here. One moment is a double bond. The next moment is a what? It's a single bond. And then it becomes a double bond. It's a single bond again. Correct? Okay, so guys, on average, right, this bond is how big? How long? One double, then single, double, then single. On average, it is like what? It's like in between, right? In between 1 and 2 is what? It's like 1.5, right? Okay, it sounds ridiculous, okay, but let me introduce an idea that's not really in the notes. Okay. One moment, okay, this bond has a bond order. Okay, bond order is something that's not really your syllabus, but it's just 2, 2 because it's a double bond. Makes sense, right? Okay. But the other second, the next moment, the bond order is what? 1. Okay, so because it oscillates between the two, okay, you can think of it as they take an average of the two. So what's the average bond order? For benzene, the bond order is 1.5. Okay, so as ridiculous as it sounds, right? Okay, it's a legit thing. Benzene is a bond order of 1.5. This guy is a bond order of 1. This guy is a bond order of 2. So its properties will also be in between that of a single bond and a double bond. Does that make sense? Yeah, so that's pretty much it for this portion. How do we explain this 1.5 bond order? Okay, because bond order is not in your syllabus, but I want you to take note. It's because of these 4 words called partial double bond character. So this is the first time you guys have seen a partial double bond. There's only, you all have learned single bonds and double bonds. But now there's such a thing called a partial double bond. Meaning, as you can see, guys, a single bond that also has characteristics of a double bond. You can see that? So it's like half single, half double. That's why you can think of it as a bond order of 1.5. And because it is a partial double bond, right? Okay, its bond length will also be in between that of a single and a double bond. Does that make sense? You know? So that's pretty much it for this segment. I need you all to highlight the word partial double bond. Okay, just to summarize again, how come double and single have the same bond length? Why are they all identical? It's because it's not double and single. Benzene exists all at the same time because of the delocalization. So it's the same bond length. Can? Yeah. Then afterwards, again, we have partial double bond character. Okay, so far. Okay, so that's the first feature. Now let's look at the second feature. Okay, benzene is a planar molecule. Guys, what does it mean when you are a planar molecule? What does a planar molecule mean? Okay, it's like flat. Okay, so imagine I have this flat piece of paper here. If I take benzene and I slap it onto this piece of paper, right? It's just gonna be flat. Nothing's gonna protrude. Okay, why is that so? Okay, this one they can sometimes ask you to justify. But why is that the case? You look at each carbon atom of benzene. They're all the same, right? What shape do they have? We mentioned just now. This trigonal, planar. The word planar is in the name already. Okay, that's why it's planar. Okay, but you can't just explain that. It's trigonal planar because the carbon is what hybridized. Yes, sp2. So if you want to justify why it's a planar molecule, number one, you must tell me that all the carbon atoms are sp2 hybridized. And because they are sp2 hybridized, then you can tell me that it's all trigonal planar. That's why the whole molecule is planar. So very easy to justify this, but you just need to bring hybridization into the concept. Okay. Okay, so we're gonna look at the last point. Okay, so I want you guys to predict first. Benzene, does it undergo addition or substitution reactions? Now, first of all, remember how we determine this. Okay, alkanes. Alkanes, guys, what kind of reaction do they undergo? Okay, they undergo FRS, substitution. Really? Okay, so guys, why do alkanes undergo substitution? Is it just random? Like God just decided that alkanes undergo substitution? Why do alkanes undergo sub? Because alkanes are what kind of molecules? They are, which one? Okay, they are saturated. Okay, the carbon atom in alkanes has a maximum of 4 atoms. Okay, add any more things onto a maximum? No. Okay, so you can only substitute. On the other hand, now guys, alkenes, what reactions do they undergo? Okay, they undergo electrophilic addition, right? But why do they undergo addition? Conversely, because alkenes are unsaturated molecules. Okay, so you can add more atoms onto the alkene. Okay, so it makes sense so far. Now we try to apply the same concept over to a benzene ring. Okay, a benzene ring pretty much is made up of double bonds. Okay, so you should expect it to undergo which reaction? Okay, you should undergo addition, right? Because you see plenty of double bonds. So should they undergo addition also? Okay, so let's talk about this. Benzene doesn't undergo addition. In fact, it will undergo substitution instead. So it actually breaks this rule. We cannot use this same rule over here, right? To describe benzene. So why on earth does benzene prefer substitution, even though it is 100% not a saturated molecule? It has double bonds everywhere. So what's going on over here? Okay, so remember, guys, these 3 properties are all linked to the delocalized pi electron count. Remember, a delocalized high electron cloud makes benzene what? Okay, extra stable, makes benzene resonance stabilized. Now, given that benzene is a very stable molecule, okay, bear that in mind first. What happens if benzene underwent addition? In fact, guys, you all remember how addition is like? If I take a double bond, a normal LT, and I just react with HBr, eventually what am I going to get? I'm just going to get this, right? Okay, I'm just going to add an H and a Br onto the LT. What happened to the double bond over there? The double bond has been broken, right? Okay, that's how addition is carried out. So you imagine this, benzene also has double bonds. If it undergoes, let's say, an addition here, it will also break a double bond. You can see that. Let's just say I break one double bond only. So I add HBr onto one of the double bonds. You can see that. But when I do this, guys, what happens to the ring? Is the ring still there? No. You are essentially breaking the ring. You are essentially breaking the very thing that makes benzene extra stable. Would you like to break something that's very stable? Do you think that's very easy? No. Okay, the reaction has very high activation energy when you do so. So let me say this again. The ring that you see in benzene is like a sacred little ring, right? Keeping benzene very, very stable. It's extremely difficult, right, to break this ring over here, given how stable benzene is. It's so stable, it's not gonna let you break that ring. Okay, it's the very thing that makes it stable. So of course, it's not gonna let you disrupt it. So guys, that's why benzene does not undergo addition, because addition will disrupt the stability of benzene. And guys, when you disrupt the stability, is that energetically favorable? No. That's why we don't actually have this reaction happening. So I need you all to include this keyword also, which is not energetically favorable. Keywords here. Okay. Addition disrupts the stability. But guys, on the other hand, you just look at how a substitution reaction carries out. I have a benzene ring over here. And guys, what's on the carbons again? Okay, on the carbons are all just invisible hydrogens, right? Okay, so how a substitution reaction looks like, it will look something like this. It's just going to swap out the H for, let's say, a Cl. Can see that? Can see this balance equation? Very simple, very, very simple substitution reaction. What do you notice when you undergo substitution? Are you disrupting the stability of that? Are you breaking that sacred ring in the middle? No. In fact, you are keeping the ring in the middle, keeping the very thing that makes benzene stable. In other words, you are preserving the stability of benzene by doing so. So as I mentioned, the delocalized high electron cloud is like some forbidden ring that you're not supposed to break. Okay, it's very difficult to break, okay, because it's very stable. So substitution helps to preserve that, which is a lot better than breaking. That's why benzene doesn't really follow the saturated and unsaturated rule. So this is a common 2-mark question they can ask, and all you need to do is to write these words, and then that's your answer. Okay, it's also written here. So those are our applications, okay, of the delocalized high electron cloud. All okay with this? Right. Those who are done, you can turn over to question 7. Okay, page 7, sorry. And on page 7, there's a bunch of options. Okay, I want you guys to tell me whether the options are true or false, and then just jot down a bit of explanation in the box at the bottom. Okay. Okay, again, if you do not know what the exact keywords are, never mind. I want you all to try. Don't just flip back the page and copy. Okay, try your best to write your own words based on your own understanding. Later, then we will correct the keywords. Not to worry. Okay, give it a try first. Not very nice. Okay, for option 3, the cyclohexatriene is just this. Cyclohexa, 6 carbons, triene because 3 double bonds. That's what they're referring to. Okay, the explanation don't have to be that long. We just need to mention a bit can already. Okay, can we go through? Right. Okay, for the first option, they said it prevents benzene from undergoing addition. The it referring to the delocalized pi electron count. Okay, is this correct? Okay, yes, definitely correct. Okay, so it prevents benzene from undergoing addition because you all need to briefly tell me, right, what's wrong with an addition. Okay, addition reactions, why are they bad? Because it disrupts the stability of benzene, which is energetically unfavorable. Yeah, okay, just give me that statement, Kevin. Okay, now the second one, why is it that the, okay, this is correct one, definitely. Okay, it's intermediate in between that of an alkane and alkene. But what's the main reason behind that? What's the main focus? What's the keyword? Why is it that they are right in between them, those two? It's not because of that. Okay, you just need to tell me the fact is it has partial double bond character can. That's more than enough to describe that. But yeah, okay, the alternating idea, don't ever write it as words. It's just for you to understand. Okay, so that's the second option. Okay, the third one, right? Okay, then I need to explain a little bit more, right? Okay, is the third one correct? Okay, this one you can just refer to the diagram we saw just now. Less exothermic than that of cyclohexatriene. Okay, the arrow is smaller, less exothermic. So remember just now, okay, cyclohexatriene, like bigger arrow. This one less exothermic, so smaller arrow. Why is this correct? It's because what does benzene have that cyclohexatriene does not have? Benzene has what? Okay, the ring, which is what's the ring called? Okay, so the benzene has this extra feature. It has a delocalized high electron cloud, which makes it what? Yes, again, which makes it more stable. And guys, if you're more stable, you have more energy or less energy. Okay, it has lower energy level, right? And since it has a lower energy level, the enthalpy change will be less exothermic. So that's the flow for your explanation. Okay, you start off at the very beginning of this. It all begins because benzene has this extra feature that cyclohexatriene does not have. Because of this extra feature, it is more stable. We mentioned just now, more stable means less energy. So it will be a less exothermic reaction. Sense? Yeah. Okay, moving on to our final option. The presence of high electrons allows benzene to be a good electrical conductor. Correct? Is it correct? Yeah, a lot of you guys will say it's correct because you see the word delocalize, so electrons are mobile. But the answer is wrong. Okay, benzene is not an electrical conductor. Because guys, again, you're not exactly wrong when you say that the electrons need to be mobile. But guys, you have to realize the electrons, right, they are delocalized. Is delocalized only within the ring, right? But if you want to conduct electricity, the electrons should be delocalized. Is it just within one molecule? It should be across the different benzene molecules. Okay, electrons must be delocalized across molecules. Okay, so which it doesn't happen over here. So you tell me, okay, the high electrons, okay, are delocalized within the ring. Okay, not across or between molecules. Okay, so you cannot forget. After all, benzene is a simple molecular structure. So it's probably not going to be able to conduct electricity. All okay with this so far? Yeah, right. Okay, so that kind of concludes like the first portion of benzene rings. Okay, why it's so special again is because of your delocalized high electron cloud. It just makes the compound very stable. So that's why later the reactions we're going to discuss are going to come back to this again. Okay, but for now we have to complete a little bit of our page 8. Okay, our physical properties. Okay, let's just recall this again. Okay, if you look at the first question, they said, why does benzene have a low melting and boiling point? Let's just answer this question in terms of structure and bonding. Okay, so guys, in terms of structure and bonding, what's the structure of a benzene molecule? Okay, it is a simple molecular structure. What's the bonding? Oh, covalent. Okay, remember, for simple molecular structures, the bonding they are referring to has to be your intermolecular forces. Okay, so it's just a non-polar molecule, right? So it's just ID attractions. And guys, you want to link back to melting and boiling points. How will you link it back to that? Weak ID attractions, okay, require very little energy to overcome, yes. And that's pretty much your answer. Yeah, say again, simple molecular structures. The bonding they're referring to, you need to specify intermolecular forces. Okay, I think the next question is the solubility question. Okay. Okay. So these diagrams. Okay, if you look at the next question, right, we are discussing solubility. Okay, benzene is soluble in CCl4, but not. Okay, so remember how a solubility diagram looks like. Okay, each molecule has interactions with one another. But when you mix them together, they will try to form some sort of interactions with one another also. Okay, with this red color interaction. You can see that. Okay, so let's explain the first one. Okay, or let's just recap a little bit of solubility. Remember, how does solubility work? Okay, so if we have a polar molecule and a polar molecule, usually are they soluble or not? Soluble, right? Okay, because polar and polar, what kind of interactions do they form? Okay, they can form favorable PD attractions, right? Both of them form the same interaction, so obviously they are compatible with each other. But is it just PD attractions? Okay, ideally sure. Polar molecules. Yes, okay, but we are talking about more dominant interaction here. Okay, it's either PD or it could be hydrogen bonding also, depending on whether it fulfills the criteria. Okay, then how about another scenario here? If I give you guys a non-polar molecule and you try to dissolve it in a non-polar solvent, is this compatible? Is this generally soluble? Yes, okay, again, what kind of interactions would they like to form here? Okay, they are the same type, so they form very favorable ID attractions. Quite likely they will dissolve with each other. Okay, but then of course we have our third scenario. If I have a non-polar molecule and I try to dissolve it in a polar molecule, usually is this soluble or insoluble? Insoluble. Okay, because once again, they are not compatible with each other. This one wants to form ID attractions, this one wants to form PDP or hydrogen bonding. It's not the same thing. Okay, so they don't mix. Make sense? We're going to apply the same idea here. Okay, so I want you to look at the first scenario. They tell us that it is soluble in CCl4. Why is that so? Okay, good. And benzene is also non-polar. And we can keep our answer shorter by just saying that they form what kind of interactions? Okay, they form very favorable for interactions. ID. Okay, both are non-polar, both can only form ID. So that's the first part of your answer. Okay, you just need to tell me benzene and CCl4 are non-polar molecules, so they form favorable ID attractions with one another. This one you don't need to mention the energy release and energy to overcome, because they're both the same compatible interactions anyway. You just add in the word favorable. Okay, what we are more interested in, right, is when they are not soluble. The other scenario, we try to dissolve benzene in water instead. Okay, what will happen? Okay. I'm just gonna write the format of answering this first. Okay, so remember your format of answering, right? Okay, we have our energy release, energy required to overcome. You must compare them with one another. Okay, all the keywords in between. Okay, but if you compare between benzene and water, okay, benzene is a non-polar molecule, as you said just now. Water, then. Okay, water is clearly polar, and you already see a compatibility issue. It's a red flag here. Okay, so how? What should we do? What's the interactions? Let's identify all the interactions. Benzene now, what's the interactions with one another? Okay, good. ID. Water is what interactions? Hydrogen bonds. And you take benzene and water, mix them together, right? What's the interactions with one another? Given that they are not compatible with one another. They are not compatible, they don't like each other. So they will form like the weakest interactions you guys know of, which is just ID attractants. Right? And then from there, okay, let's just fill in our answer. Okay, energy release from the what? When we talk about release, we're talking about what interactions? The purple one, sure. Okay, when you all release energy, you form interactions or break interactions. You form interactions. Where are the form interactions? It's the red one. Okay, what you want to break is the existing purple color interactions between each molecule. So we are going to first discuss the red color ID attractions between benzene and water. Okay, so it is what to compensate. What's the keyword there? Okay, insufficient, because they tell us already that it is insoluble. Okay, compensate for energy required. Same thing, guys. You require energy to break bonds or to form bonds. Okay, you want to break bonds, right? So you require energy. So you want to break the interactions. They try to break the purple color interactions here. Then you just label it. You have insufficient energy to break the ID in benzene and the hydrogen bonds in water. Done. Can see that? Okay. So once again, our solubility questions. Okay, we've done this many times before. Okay, this just serves as a recap, right? Okay, so that now that we've gotten like the fluff out of the way, right? Okay, now we can go and look at the mechanism drawing and all that reactions and stuff. Okay, but so far, any questions? Okay, so we have gone through physical properties, which is not much. Okay, we've gone through the special parts of a benzene, the properties. Okay, now we're going to look at what reactions benzene now can actually undergo. Okay, so turn over to page 9. We're going to look at this reaction here. Okay, just now we mentioned already, benzene undergoes substitution or addition. Which one is better? Benzene likes to undergo substitution, right? Okay, so we are going to look at electrophilic substitution. Let's just recall a few terms of that. Electrophile. Electrophile is what? Okay, good. It is an electron poor species, and an electron poor species usually has a what charge? Okay, a positive charge or a partial positive charge. Okay, these constitute as electrophiles. Now remember, how do electrons move in organic chem? From where to where? Rich to poor. Okay, good. So recall all our special features rich attacking poor. So somehow we're trying to attack the electrophile which is poor. Okay, so you all take a look at the first reaction here. Okay, it's called nitration. Okay, because I'm gonna take a benzene. Okay, remember there's H on every carbon. But I'm just going to specify one H, okay, just for you to see. If I react with HNO3, okay, what's going to happen is I'm going to substitute the H with a OS NO2. Then there's also other byproducts. You can see that? Okay, now the reagents and conditions go and highlight. It's quite special. Okay, first you need concentrated HNO3, obviously. But you need concentrated H2SO4 as catalyst. You'll see what the catalyst is used for. And finally, we will need to use warm conditions. Now in the notes, they specify 55 degrees. Okay, or you can use warm also can. Okay, I'm just going to write both down. Okay, warm or 55 degrees. Yeah, you need to memorize this. Okay. But notice a few things first. Okay, we're going to draw the mechanism, right? Okay, and understand what all this is for. Okay, so turn over to the next page. And then again, now guys, what's the first thing you must always draw for a mechanism? What's the first thing you write down? Again, the title, the name. Yeah, okay, we're going to write it down first. Electrophilic substitution. Okay, we already justified why is substitution. Now we need to justify why is there electrophiles, right? Okay, so write the title first, electrosub, write the whole thing. Okay, so this reaction is going to be split into steps. Okay, it's quite a big reaction. Okay, but for the first step, I want to name you're going to write the rationale behind that step. Okay, so for the first step, my job here is to generate a stronger electrophile. We'll come back and explain this later. But I want you guys, again, this first reaction here, unfortunately, no choice, we need to memorize the equation. Okay, so what's going to happen is this. I'm going to take HNO3 and I'm going to react it with the catalyst. 2H2SO4 is to balance. And then what's going to happen here? I'm going to get NO2 plus 2HSO4 minus. And I'm also going to get H3O plus. Again, this reaction here is one of those very few things where I tell you guys just straight up memorize. Okay, there's no way you can come up with this equation yourself during the exam. Okay, because we do not know how this reaction works. All we need to know is that the reagent reacts with the catalyst, okay, to create a stronger electrophile. Okay, guys, can you all just tell me what's the electrophile here that I'm interested in? Who am I trying to generate actually? NO2 plus. Okay, I know there's a plus here, but don't just blindly tell me that's the electrophile. I want this guy because eventually that is what's going to be substituted onto this. So go and highlight this guy. This right here is your stronger electrophile. I'm trying to create this guy so that it can react. Okay. Now, before I move on to the next step, right? Okay, any idea, guys, why is it that I need to create a stronger electrophile? If you look back at alkenes, for alkenes, I can just take my alkene and just instantly react with my HBr. Right, very simple. Okay, how does the rich attack poor here? Who attacks who? Number one attacks hydrogen. Okay, so hydrogen is rich or poor? Poor. Okay, rich attack poor, so hydrogen is poor, so H has a partial positive charge, right? Now guys, you notice this, the electrophile in this case is H with this, right, partial positive charge. You can see that. Okay, but now the electrophile doesn't have a partial positive charge. It has a full positive charge. Which one do you think is stronger, partial or full? Obviously full, right? Okay, you can see the difference first. Now the question is this, we're going to answer this later after we finish the mechanism. But let me just pose this question first. Why is it that alkenes are just a weak electrophile settle rate? Now for benzene, you need to make such a strong electrophile for it to react. What's the simple answer to this question? Exactly. We already mentioned why benzene is such a special little guy, right? He's so special because he is very stable. Because of what again? What makes him very stable? Delocalized high electron cloud. It's because of that, right? Benzene is so stable. Now, if you're very stable, right, can a weak little shit like this guy react with benzene? No, okay, too weak already, too shit. You need something stronger, okay? And in order to make this stronger electrophile, that's the reason why we actually have catalysts. Can see that? Okay, so we discuss this first, later we write down the explanation. Okay, but now, okay, for the second step, I'm gonna finally, right, take my benzene ring, and I'm gonna react with who? Who am I interested in? I'm only interested in my NO2, right? I don't care about the rest. Okay, so I have NO2 plus over here. Now remember, guys, I usually say the plus charge to place on the correct atom, but you can actually place it on the top right corner also. Okay. Now, guys, want to make a guess? Who is rich and who is poor here? Rich is who? Obviously benzene, because this guy's poor, right? Okay, why is benzene rich? Because again, he has a freaking high electron cloud, a cloud of electrons. Okay, so he's rich. What I want you guys to do is this: point from the benzene, the ring, because the ring is rich, and point towards who? N or O. Okay, it has to be N. How do I know I'm pointing towards the N? No, this is not radical, this is a cation. But how do I know N is poor? How do I know I'm attacking N? Can I look at the overall equation? Is the benzene forming a bond with N or forming a bond with O? Forming a bond with N, right? Okay, so I want you guys to always look at the overall equation. I'm forming a bond with N, so no shit, I need to attack N. So guys, if you want to be very specific, let me just mention this. Your plus charge should be on red. Okay, it should be on N. N is actually the one with the plus charge. N is poor. Okay, I mean you can put it on the top right, but I want you guys to know the precision in drawing mechanism now. Okay, so over here, one arrow up. And then from here, what's going to happen is this. You'll just look carefully, right? The ring that attacks the NO2 is going to break partially. And there's going to be a plus charge inside. Why plus? Guys, when do you have a plus charge? When do you have a minus charge? When you gain electrons, what charge are you going to get? A negative charge. When you lose electrons, what charge are you going to get? Positive. Here, can you see that benzene is sacrificing his own electrons in the ring to give, so it's losing luck. That's why now the benzene has a broken little ring. But now you're going to form a bond with NO2. But at the same time, is there anything else there? There is a what that you don't see. The H has been there and nothing has happened to it yet. It's still clinging onto the benzene for dear life. Notice this? Okay. So guys, this is a carbocation. The same intermediate we're going to saw in the previous topic. It's still a carbocation. Just a very weird looking carbocation as you can see. Okay. Right? Can Okay guys, you look at the final product. What must go? Okay. The positive charge clearly must go, definitely. But is there something else that must really be difficult? The H. He's no longer there, right? Because guys, this is a substitution. The H must leave. It's like when you break up with someone, you better leave, get out of your life. It is like a psycho dude, right? Who doesn't want to leave. He keeps coming back to the rescue. Okay, same idea over here. He needs to leave for good. How do you make him leave? Okay, so that's when you have your third step. Okay, take out your third step. Alright. Just gonna copy and paste the same guy inside. Okay, so this H has to go. Something must steal away the H. Who is there to steal the H? Really be someone rich or poor this. No, okay. There's only one H for each carbon. You can only form 4 bonds, right? Okay, the H has substituted away with NO2. It's a substitution reaction. So the H must go. Does that make sense? It must be swapped out. That's why there's no more H. Okay, C6, H6. Each carbon only has one H. Okay, you can see that? Alright, this guy somehow must go, the H must go. Somebody must come and steal him away. Who do you think? Okay, should it be a nucleophile or electrophile that comes and steal away the H? Something must attack him.
Nucleophile.
Nucleophile, right? Can see why? Okay, if I'm trying to attack H, this implies from rich to poor, right? Rich attack poor, so something must be rich. Who's rich? Okay, well, let's look at this entire mechanism here. Is there any rich to it? HSO4 minus. Minus charge implies it's probably a rich species. So, go and draw out your HSO4 minus. Rich is negative. Yeah. And guys, I want you to pay close attention to this. I want you guys to draw the lone pair on O, not on S. That's just a mistake a lot of people make. I made this mistake last time also. I was like, student. Okay, so make sure it's on O. Okay, now the lone pair on O must attack H. So you can see, okay, if you want this person to live your life, right, you must go and chase someone else, must be interested in someone else so that you can live your life. Okay, so attack already, okay, good. What do you think you're going to form? HSO4 minus H. What are you going to form? H2SO4, right? You just get back another H. Okay, so one of the byproducts over here is going to be H2SO4. And of course, I need to get my final product. It's the last step already. I need to get my final product. Okay, there's a few things that I need to do here. The H must go, it's gone already. But I still need to fix the ring, right, guys? The ring is broken there. I need to repair that shit. Okay, how do I repair the ring? Look, is it rich or poor? Currently, the ring is poor as shit, right? He wants electrons. Now when H go already, what should these electrons do? Yeah, just give them. This guy needs it. The electrons not doing anything. So just give the electrons into the ring. So you must start from the line. Do not start from H. H, you have electrons on. Okay, it's the line, this bond over here from these electrons. Point from there into the ring. That's how the ring is repaired. You can see that? It's to the ring / positive charge. And that's the end of the mechanism. Still have one more thing. Okay, that's the end. Can someone just make a guess? Where's the slow step? And usually it's the first one, but look at it closely. Second step. Yes. Yes. Yeah, okay, good. Okay, this is the second step. Any idea why? Wait. Why is the second step? In the okay, remember, don't see the link there. A slow step is a step that has high what? High activation energy. Okay, so slow step, high active. Why does the second step have such a high activation energy? Can you just tell me what's going on over here? What are you doing to the ring? You're breaking a ring. And did we mention just now? Is that easy? Actually, it's difficult. Okay, it's very difficult to disrupt something that gives the benzene its state. So that's why this step is high activation energy, because we are disrupting the stability temporarily. Of course, later on we'll need to fix the ring. So temporarily disrupting it, right? Very, very unfixable. Okay, that's why high activation energy. Can see this. Okay, Now a few more features we will talk about also. Okay. Okay, so far. Next question. Can you remember benzene, planar or non-planar? Benzene is a planar or non-planar molecule? It's planar, right? But does it stay planar throughout steps 2 and 3? It turns into this thing first, right? Then it turns back into your whatever this is. Okay, this planar obviously is a benzene ring. The final product, is it planar? Okay. Okay, perhaps we don't look at planar. Okay, why is, let me rephrase this whole thing again to be more specific. Let's focus on the carbon, not the whole molecule. Okay, when the carbon is what hybridization. Okay, it is sp2 hybridized, right? All of them. Now, does that carbon, let's just focus on this carbon. Since this carbon underwent a reaction, does this carbon remain sp2 throughout reaction? No. This is sp2, right? What happened then? Yeah, okay, what shape is this? Exactly. You can see that in the carbocation intermediate, you will see a tetrahedral carbon. And tetrahedral carbon is what hybridization? Sp3. And guys, that's why I talked about planar just now. Is the carbocation a planar structure? No, because tetrahedral is not planar. So that's why, guys, this is a very common MCQ question. They will ask you guys if the carbon remains sp2 throughout. And the answer is definitely no. It turns from sp2 to sp3 and finally to sp2. Okay, back to trigonal. This is normal, the normal benzene. All the carbons here trigonal. Can see that? Okay, so that's another feature here. Okay, sp2, sp3, then back to sp. You can write it down. What's happening? So, freaking war. Yeah, what the heck? Okay, to enable the carbon, this carbon here, tetrahedral, right? Now, guys, one more final question. Just now I mentioned here H2SO4 is a catalyst. How do you see that is a catalyst based on this mechanism here? What's the property of a catalyst that you notice from here? Yes, is that you see you start at the start is regenerated at the end. You're going to do that now also. They regenerated as a catalyst. Yeah, you see that? Okay. So the next page, what's that? Oh, okay. Right after this, turn over the page. In E11 has a box there. I'm going to read through that. We briefly touched on that just now. Okay, read through it first. Okay, see they're saying that electrophilic addition of alkenes. Did we have any nonsense catalyst in the topic? No. But how come this benzene need to add one catalyst? What was the simple explanation that we went through just now? Okay, benzene is a very stable compound. Okay, let's just simplify this first. Benzene is way more stable than alkene. Because what does benzene have that alkene doesn't have? Delocalized high electron count. Because it is so stable, how does a catalyst help? How does it help? What does it do? Okay, okay, lower the activity, but how exactly? In particular, right, what is the catalyst actually doing in this mechanism? The purpose is to, okay, just now the purpose was an electrophile with a partial positive charge. Is that enough to make a benzene react? No, not enough. So that's why a catalyst comes in to generate a stronger electrophile. You have a species now with an actual full positive charge. That's a lot more reactive. You see that? Okay, so that tie everything together. Okay, so that's the answer. Let's just write it down here. Okay, so number one, okay, alkenes, okay, have high electron count, okay, that can react with electrophiles with a partial positive charge. Okay, all we are saying is that alkenes are nothing special. As long as there's a poor partial positive charge, you're just going to react with it. Okay, but now my focus is on benzene. Benzene, however, it has a delocalized high electron count. Okay, which makes it extra stable. So the normal as electrophile are not enough, too weak. Okay, so thus a concentrated H2SO4 catalyst is needed. Okay, but you must tell me why is to generate a stronger electrophile, NO2 plus. So just now I mentioned partial positive 2 weak. So I will mention it in my answer. Now, why is this electrophile stronger? Is because there's an actual positive charge inside. Okay, and you must give me the reasons behind it. Okay, because it's very, very stable. Okay. Okay, if not, the rest of page 11 and 12 already discussed. Right? Okay, any questions? Nope. Okay, we're gonna try a few more mechanisms. Okay, can you all turn over to page 13? Okay, so just now we substituted NO2. Now we're gonna substitute halogens. Okay, the equation here is gonna be slightly easier. Okay, so you take a look at my equation first. I'm gonna substitute Cl2. Okay, and what's gonna happen is H becomes Cl now. Simple as that. Okay, look at the reagents and conditions. Okay, I have Cl2 gas, but just like before, I need to add a catalyst. So my catalyst here, take a look, it's AlCl3. You might also see FeCl3. Both are fine. Later we'll understand why. Okay, but this catalyst okay, is anhydrous. You all know what anhydrous means? Right, yes, okay, no water. Okay, and if you lazy write anhydrous, you can write solid state. As long as not aqueous can already now. Okay, so solid means no water. Okay, so I put an AlCl3 catalyst and finally warm. Okay, so we look at our overall equation, our reagents and conditions. Now let's try to draw the mechanism. Okay. Now first of all, do you think Cl2 okay, Cl2 with a partial positive charge, is that enough? No, okay, benzene needs a full positive charge. So that's why the catalyst is added again to create a stronger electrophile. Okay? Okay, how does it work? Cl2 reacts with the catalyst that you add inside. Guys, how does this work? What is the electrophile you're going to get? What electrophile do you think I want? Give me a guess. Okay, just now, remember, just now I substitute NO2, my electrophile was what? NO2 plus. Now I want to substitute Cl, so my electrophile is Cl plus, yes. Okay, it looks weird. But guys, notice whatever that I substitute, right, just get the electrophile out. So somehow I can get Cl plus, but what will be my other compound? AlCl4 with what charge? Minus, because you will need to make sure it's overall neutral. Now, how does this actually work? Okay, I want you to take a look at a little bit of arrow movements. Now, if you don't write any arrow movement, it's fine, but I want you to see how it works. So Cl2 looks something like this right there. Okay, what's going to happen is this. Somehow, one of the chlorines is donated to AlCl4. AlCl3, sorry, to become AlCl4. Now, in the notes, they also mentioned this guy is Lewis acid catalyst. Guys, what is a Lewis acid? Can you remember? It's not about H plus. H plus is Bronsted theory. Lewis acid is about what? Nope. Electron pairs. Good. So Lewis acid will accept electron pairs. And this is especially important in this portion here. How does it accept electron pairs? Why can it accept electron pairs? Guys, can you all look at AlCl3? How come it can accept electron pairs? Not enough, right? How come it can accept even more? AlCl3. How do we explain this? Okay, it's not that it can expand octet. Right now, how many valence electrons are there around at the medium? Okay, there's 6, right? But the magic number is what? Okay, 8. There is a vacant orbital. Aluminium has, okay, unfortunately, only has 3 valence. So you can have a vacant orbital that can accept a lone pair. You can see that. That's why we choose aluminium over here because it's a perfect Lewis acid catalyst. Okay. It is a vacant orbital to accept a lone pair from who in this case? One of the Cls. Okay, so what's going to happen is this: one of the Cls, right? The electrons here is going to go straight up into the aluminium. So that's why the chlorine on the right is going to bond to the aluminium. You can see that. But how about the guy on the left? Can you see he has just lost electrons? If you lost electrons, you must gain a plus charge. Look at your aluminium. He just accepted. Guys, if he gain an electron, what charge does he have? Just gain electron back. So he must have what charge? Negative charge. See that? Okay, so it all works out. Okay, all our rules will stay consistent. Okay. Now with that said, okay, again, you don't need to draw these arrows just for your own information. But now that I've gotten what I want, finally now I can take out my benzene. And I'm going to take out my Cl+. Guys, how do the electrons move again? From where to where? Okay, your benzene to Cl. See the arrow, very simple. Just like that. And from here on out, right, everything else is the same. So I want you guys to try the mechanism. Similar as before. Yes, the H must be drawn because you are showing the electron movement of H later on. Not really thick, right? You get another two more. Three products. Yeah. Yes, you're missing that. You're missing that. You're correct. Okay, so notice, guys, when you just look at my answer, again, you break the ring. Okay, then basically the broken part, guys. The broken part must face the place at where the reaction happens. Okay, so here the Cl, then H. Okay. Now just a few things. Okay, the third step, right? Take note, you want to take AlCl4 minus because he's rich, but the lone pair must be on who? Al or Cl. Okay, lone pair must be on Cl. Okay, why? Because remember I drew this just now. AlCl3, 6 valence electrons, no lone pairs. Then when he accepts the fourth one, right, it's via a native bond like that. He still doesn't have a lone pair. Okay, so it's this guy that has the minus charge bar. Okay, so in other words, okay, over here what's happening? Attack H, electrons from the bond, start from the bond, go back into the ring. Okay, okay, but remember, H and Cl will combine to form HCl and AlCl3. You cannot combine everything together because I want to see AlCl3 as a byproduct. You see that? Okay, and of course, don't forget your slow step. You don't write fast, it's fine now, but make sure your second step is smooth. Right? How got that light green flavor? I don't see here. The different way. I don't know. Okay, come, turn over to page 14. Almost done. Okay, we will later do one more question, then we can take a break. Is it the same thing? I don't know. I thought it was the same thing. I mean, hey guys, turn over to page 14, right? Okay, let's answer this question. Just now we mentioned that this catalyst must be dry. Any idea why? To answer such questions, you must ask yourself the contrary. What happens if you make it wet? Okay, so this is how you answer questions in future. What happens if there's water? Something bad must happen, right? That's why you don't use water, right? Dissolve. No, it doesn't dissolve. It doesn't dissolve. Okay, so here are some clues. If there's water involved, okay, and there's something to do with the Lewis acid property. Okay, the fact that it's about accepting electron pairs. Okay, so just now, AlCl3 is accepting an electron pair from Cl, form Cl plus. Fulfills my objective of creating a stronger electrophile. But now, what happens if there's water? Exactly. That's the answer. It can take a lone pair from water, right? And in fact, there's a higher chance of taking the lone pair from water because water is usually a lot, right? So if it takes a lone pair from water, then then it can't form Cl plus, which is the exact reason why I added AlCl3 in the first place. It's so that I can form Cl plus. So you're basically ruining AlCl3's sole purpose of forming Cl plus. Can see this? Okay, so let's answer here. Water will be able to donate its lone pair of electrons, okay, to AlCl3. Okay, but yeah, writing this is definitely not enough. You must tell me then what happens. What's the underlying thing that's bad over here? This will prevent Cl plus from being generated. So next time in MCQ, if they go and put it very sneakily, go put it one equals, right? Study wrong. Everything else can be correct, but then here they're going to put equals, right? Out. Whole option is wrong. Okay. Okay, any questions so far? Oh, good. Okay, can you all turn over to page, what's this, 16? Okay, there's a question there. Give that a try. Right? Okay, they want you to describe the mechanism, whatnot. Okay, it's the same as before, draw arrows and all that. Not Cl plus. Okay, guys, how do you know which one to pick? If you notice, now we come out with this thing, right? ICl, what's the difference? Who is more electronegative? Cl. And because Cl is more electronegative, it's the one that gets watered away. Remember, I want to create an electrophile. ICl, I is less electronegative. He is already on his route to becoming an electrophile. But is this strong enough? No. I'm creating something stronger, which is I plus. Cl is already stealing electrons towards himself, so it cannot be Cl. Okay. Okay, so the first sentence should be like that. ICl plus AlCl3, right? The electrons will be tagged along with your chlorine. Okay, so it's I plus and AlCl4 minus. Okay, just fix your answer. Very good. Okay, guys, let's continue. We're gonna end off right after this. Okay, with maybe one question here and there. Okay, guys. Before we move on from this, there's actually one more thing I need to discuss. Okay, so just now, right, we have this AlCl3. The rule is the electrophile should be the less electronegative atom. So you're gonna get I plus, basically. Okay. But a lot of people think that, oh, is it because this is AlCl3, so the Cl can combine with Cl to become AlCl4? Now here is just a pure coincidence. Okay, let me give you guys another example. If they didn't give you ICl, they give you IBr instead. Can the catalyst still be AlCl3? Yes or no? Okay, some of you will say no because it should be like Br3, right? But I want you all to take note. When this happens, right, the Lewis acid function of accepting electron pair is the Cl or the Al. Who is the one actually accepting the electrons? It's Al, right? Al is the one with the vacant orbital. Does Cl actually matter? So guys, over at this question that you just did, can I use AlBr3 instead? Does it change anything? No. Okay, you can use AlBr3. Again, it doesn't matter. Because the whole purpose of this is for Al to be a vacant orbital, so you can accept electron pair. You want to use AlI3 also can, whatever. So if you change all this to AlBr4, it's all fine as well. Okay, now guys, if you take a look at this, if I use IBr, can I still use AlCl3? So I repeat the same question. Is this still possible? Yes, because Al is the one still accepting the lone pair of electrons. Cl doesn't matter. It can be anything. So all I'm trying to say is this one. It can be AlX3. Doesn't matter what it is. Okay, so let's just say I use AlCl3 now. Okay, let's try to write down the equation for this. Okay, if I take IBr and I react it with AlCl3, what would the products be? Again, the less electronegative is I, so it's I plus good, followed by Br and minus good. So guys, it doesn't matter. Okay, and then towards the end over here, right? What would the answer be? Okay, because there's a big fact, AlCl3 Br minus, right? Where does the lone pair come from when you draw the arrow? Cl or Br? That's the fact. Okay, YBR, that's correct. Because what I'm going to form here, HBr, so that the other product is AlCl3. This guy needs to be regenerated, so choose wisely. Br is the one that goes back, this AlCl3 needs to be regenerated. Okay, that. So that's answer for this. Okay, it can be anything. Okay, it's always the less electronegative atom. Okay. Now we're going to look at one final scenario for electrosub. It's only on page 17, then we're going to stop there for today. Okay. So for electrophilic substitution, I'm feeling water splashing. No, am I tripping? I think since I can't be. Okay, but anyways, okay guys, the first one that we went through just now was nitration. Now guys, never use nitration as the type of reaction. It's always electrophilic sub. Okay, nitration is your NO2 plus. Then we got halogen, so they call it halogenation, which is your X plus. Okay, last one is going to be called alkylation. Guys, what's an alkyl group? Can you remember, right? An alkyl group is anything that has a carbon and hydrogen. That's called alkyl group. Okay, so alkyl groups are also known as R. So now we're going to use R plus. Now the full name for this, as you can see, is called Friedel-Crafts alkylation. That's just the name of the scientist. We don't care about that. Okay, just focus on the word alkylation. And with that, right, we're going to try to draw a mechanism. Okay, now first of all, right, okay, we have to look at the overall reaction first. Let's just say I have a benzene and I want to suck in an alkyl group CH. It is entirely possible for us to suck the H with a CH3. But what do we add over here? Okay, so take a look at the reagents and conditions. If I want to suck CH3 inside, I'm going to add CH3 with a Cl. And then my catalyst here, I can just add AlCl3 catalyst. And then of course afterwards, okay, you warm it also. Okay, then afterwards you can get HCl as a byproduct. This is the overall reaction. And I want you all to try to draw the mechanism for this. Okay, I got you guys through. How do I generate the stronger electrophile? In fact, guys, what is the electrophile that I'm interested in? What is the electrophile that I'm trying to get from this reaction? Good. I want to sub CH3, so I have CH3 plus as my electrophile. But where does that come from? How do I get CH3 plus? I get CH3Cl, and it must react with my Lewis acid catalyst AlCl3. That's how I form CH3 plus and AlCl4 minus. So as you can see, this is the same as before, same as the second example. If whatever alkyl group you want to substitute, just add a little Cl or halogen, whatever halogen inside, and you'll see. Guys, does it have to be AlCl3? Can I use AlBr3? Can also, doesn't matter. Okay? So here Cl, here Br, doesn't matter, doesn't have to be uniform. I just make it the same because it looks nice. Okay? Now next. Now that I've gotten my ClCH3 plus, what should I do? Okay, the mechanism is going to be the same from now. Okay, so just going to try. Okay, try to draw a mechanism. First step, no need. Just show me the mechanism. Okay, let's try your mechanism on the board. Now, a few things. I want you to make sure that you are bonding to carbon. Attack carbon, not H. Okay, because you're only forming bonds with carbon at the end of it. Okay, so hit the carbon. Okay, of course, carbon is the one with the positive charge, but you can put it at the top right. Okay, then the rest is pretty much the same. Okay, but let's not end it off just here yet. Okay, there's still some things to talk about. Guys, and just now I already mentioned that alkylation is to place an alkyl group onto the benzene. You can see, you can just add any amount of alkyl groups on the benzene, right? Does an alkyl group have to be one carbon? How big can an alkyl group be? Can be 3, can be 5, can be 100. You can add any number of carbons, right, onto benzene using this method. Can see that? Okay, but it just depends. So guys, I want you to try this as well. If guys, I want to substitute 4 carbons, a 4-carbon alkyl group onto benzene, how will it look like? What would my equation be? Okay, so you see this, my benzene, I want to suck in 4 carbons. Let's draw in some skeletal formulas. Okay, because as the number gets bigger, okay, need to use skeletal. If I have 4 carbons on the benzene, it's just like that, right? 1, 2, 3, 4. You can see that? Okay, I can substitute that big of an alkyl group. It doesn't matter. It's just called alkylation. I just need to make sure my reagent that I add is correct. So guys, what is the reagent over here? Can you all try? Okay, what reagent would you add over here, right, in order to get that structure? Okay, assuming you also have your catalyst involved, AlCl3, warm. What is the structure here to add? Okay, go and try to draw this inside. Okay, what would the compound be? I want to sub CH3. So just now I add CH3 or Cl. So what should I add over here? 4 carbons with a
4 carbon group, right?
again 4 carbons like that with at the end Cl.
Why?
Because we need to use that's the original compound first before we can form the electrophile. So guys, maybe go one more step. I want to focus on the first step. The mechanism, third step, I don't care. First step, you form the stronger electrophile, right? You take the 4 carbons with the Cl on the first carbon, and you react it with what? It reacts with what? AlCl3. What will you form? I'm going to try. How does the electrophile look like? Right?
That thing was.
Okay, yeah, okay, try to draw it out. Okay, so see the idea, the moment the number of carbons increase in size, you all get a bit more confused really. Okay, but it's all the same principle. Okay, so how does the electrophile look like? The Cl is gone, right? So now it is the first carbon here that now has the positive charge. Can see that? Does that make sense? Okay. You are substituting, you see the final compound now. It's on the first carbon that's getting substituted. The first carbon should be the one with the plus charge. As you can see here, the first carbon has the plus charge. You reverse that process, now that means the first carbon must be the one with the Cl. I'm going to give you guys more examples. Try to write this down also. Okay. If let's just say I have benzene, what is the reagent I need to add in order to form this as my final product? I suggest you number the carbons like what I did over here. Circle the carbon, right, that's bonded to the benzene. I write this structure inside. Okay, assuming I also have my AlCl3 and my warm. If you want to write down the first step of the formation of the electrophile, go ahead also. Okay. Okay, this is very common. Okay, they can give you any kind of outcome group. That's why I want to prepare you all for more scenarios. Very common question in exam. You just need to fill in the reagent to use. Yeah, this particular structure but is very, very common. Okay, can you get an answer? Answer here is this, the CL here. Okay, look carefully. Okay, so you all had a lot of extra stuff. Okay, take a look. How many carbons are there here? Three. 1, 2, 3. Which carbon is the one that has the CL? Carbon 2 is the one that's attached to benzene, right? Okay, so that's why you see this. This carbon 1, this 2, is this 3. 2 is the one with the CL there. Okay, you can't see this, look at the first step. If this here is your desired product, how does the electrophile look like? Where's the plus charge? 1, 2, or 3? Where should the plus charge be? It has to be on 2, right? Okay, so if you want to form the electrophile, okay, I add my AlCl3, I got AlCl4 and whatnot. My plus charge has to be on the second carbon. That means the chlorine should also be on the second carbon. Just add it back. That's the answer. Okay, so it doesn't matter how the structure looks like, right? We can try another question in our tutorial. You see this? Okay, give you all 2 examples here. Okay, you all turn over to the tutorial now. We try this tutorial question and then we are done for. Anyone still clueless with this? Okay. Use numbers. Okay, if you don't use numbers, it's a bit harder to see. Okay, that's why I really highly recommend numbers. Those who are done, turn over to the tutorial question 7. Okay, we need to draw one mechanism and we are done for today. Okay. Okay, a few things that I want you all to do for question 7, okay, before you start. Okay. Just look at the overall reaction here first. Now this thing here, okay, page 7, right? Take a look at the overall reaction. Now from the question, right, they say like benzene, furan reacts, blah blah blah. Okay, so basically this thing here is called furan. It can react the same way as benzene. So just treat it as a special benzene. Here, it's like a kid who is a little bit on the spectrum. It's the same thing. Okay, it's a kid, it's a little bit special, looks a bit different. Okay, so the idea is this, okay, perhaps maybe when you all draw the answer, right, then just draw a ring inside. You need to draw the double bonds. Okay, at the same time, guys, you all see right here CH2 whatever. Can you all change this guy into skeletal? Again, I want you guys to do skeletal formula. Change this into skeletal formula, draw that first. Okay, then the overall reaction. Look at where the guy is being substituted. Again, there's a ring here. Okay, look at where the guy is being substituted. Same thing as just now. I want you all to draw skeletal for the product. Okay, skeletal for here and skeletal for product, both. Okay, cover that first. Okay, once you have done your conversions, okay, then you can start your mechanism drawing. in the CH3 with bracket 2 implies the branch. Okay, slowly convert it to skeletal first. Let me check this. What's correct there is no correct. Yeah, it's correct. If you don't, just make sure you draw the same thing. Yeah, it's fine. Yeah, it's correct. It's correct. We draw the skeletal version. It's fine. Yes. Okay, you have converted it. Sorry? Yes, correct. It's not really a triangle, but it's bonded to one carbon, then 2 carbon, 3 carbon. 1 carbon, 2 carbon, 3 carbon. It should look similar to your reactor now. Remember, we did the exercise just now. Okay, then try to draw a mechanism. Try to draw skeletal. I want to just stop. The electron part is similar to the exercise we did. It labeled the 1, 2, and 3 carbons. Okay, remember what we did just now? Okay, carbon 1, carbon 2, carbon 3. Carbon 2 is the one bonded to the benzene. Okay, and it's corresponding here carbon 1, carbon 2, carbon 3. Carbon 2 is the one with the Cl. So it's carbon 2 that has all the actual atoms. No, it's not CH3 plus because look at what we're attaching over here. Yes. Hey, remember we went through just now. The carbon that you circled out is the carbon that has the plus charge, and it's the carbon that also has the halogen. It's that same carbon. Yes, the break is the break.
Huh?
It's just a weird looking benzene. Okay, don't worry. Okay, don't be excited. Okay, guys, you notice this? Can get the first equation, the generation of the electrophile.
Yeah.
Okay, once this is done, okay, take the ring and you must point from the right hand side, because you see, the reaction happens on the right. Okay, so attack the carbon with the positive charge. Do not attack the plus charge. You see how I draw very carefully. Okay, attack the carbon, not the carbon with the plus charge. Okay, then afterwards, again, this is the slow step. Okay, you will notice this, the ring will break, and guys, the broken part should face this carbon, because this carbon is the one that has all the bonds bonded to it. Okay, from there, remember guys, there's an existing H, just like a normal benzene, and then there's also bonded to the second carbon there, like that. Can see that? Okay, you're bonding to 3 carbons, just bonding to the middle carbon only. Draw 3 carbons, you're bonding to the middle only. Okay, the H is still there. From there, you bring that down here.
You know what happened to your
It will be repaired at the end. This one? That is attached to it now.
so the positive got transferred?
Yes. The carbon has received electrons. Receiving electrons will make you a bit richer, right? So he's poor. Now he gains a negative charge. Negative and positive becomes neutral. So this carbon is now neutral. But at the same time, this guy is losing his electrons. So now he's the one with the plus charge. So the plus charge isn't transferred per se. It's just now at a different position. Okay. So same thing AlCl3. Sorry. Okay, the H has been there throughout, just like a normal benzene. Yeah, okay, so you all notice I go and make the benzene look a bit special only, right? Then everything starts to fall apart. This cannot happen in the exam, because they love to change things up like this. It's just a normal benzene. Just apply whatever we've been doing just now into the same reaction. There's still a H there, just like a benzene. Okay, so it's just that now, just now I give you all practice for all the different types of alkyl groups. Alkylation can be difficult because you are unable to see which alkyl group it is. So go and number them. Okay, from there, okay, your AlCl4 attacks the H. Some go back into benzene. It's the same as before. Okay, then now the H is gone, right? The ring is repaired. Okay, the H is gone, the ring is repaired, then you only have this. Okay, alkylation, I know it's a little bit more challenging. Here it is. Okay. Okay, we'll practice more alkylation the next lesson as well. Okay, but next lesson we're going to cover a lot more things as well. Right? Okay, any issues here? Okay, can on. Right. Okay, go check answer. If not, that's about it for today.